In this module, we will be discussing equilibrium of concurrent forces in a plane. Let's consider we have a force system with multiple forces that has a resultant R that replaces the forces in the system, as we already discussed. The conditions for equilibrium state that when the resultant of a force system acting on a body is 0, the body is in equilibrium. The body will either remain at rest, if originally at rest, or in motion, if originally in motion. In this module, we are concerned with only the equilibrium of bodies at rest. Methods for finding the resultant of concurrent force systems can be used to solve problems involving concurrent force systems that act on bodies at rest. In separating a body from its surroundings, we make use of the principle of Newton's third law, which states that action equals reaction. So, if a body A exerts a force on body B exerts a force on body A equal in magnitude and opposite in direction with the same line of action. Newton's third law cannot be mathematically proven. It agrees with intuition. Deduction from the third law agrees with experiment. Let's consider a block attached to a cable that is supported by the ceiling. Force F1 represents the force exerted on the cable by the block. Reaction F2 is equal and opposite, representing the forces exerted on the block by the cable. Force F3 represents the force exerted on the ceiling by the cable. Reaction F4 is equal and opposite and represents the force exerted on the cable by the ceiling. Let's look at the diagram after we dismantle the cable and the block. The forces acting on the cable and on the block are shown in these two figures. As you can see, forces F1 and F4 do not constitute an action-reaction pair because they act on the same body, which is the cable. So, the same is true for forces F2 and the weight W that act on the block. Both cable and block are in equilibrium, with F4 equaling F1 and F2 equaling W. Thus, F3 equals W. The cable can be thought of as transmitting the weight of the block from the block to the ceiling. A sketch called a space diagram, or free body diagram, may be used to describe the physical problem to be solved. Statics involves the forces or interactions of bodies on each other. The bodies must be separated from each other so that unknown forces may be determined. A free body diagram showing the forces acting on the body is then drawn. A free body will be isolated, and all forces acting on the body will be shown. Among the forces to be shown will be the weight. The weight of the body acts through a point called the center of gravity of the body, which is directed from the center of gravity downward toward the center of the Earth. For a uniform body, the center of gravity is the geometric center of the body. For non-uniform bodies, the center of gravity's location is usually designated as CG, or by the symbol of a circle divided up into 4 sections with the upper left and lower right sections shaded in. Clear and accurate free body diagrams are very important to the analysis of problems in static force equilibrium. The purpose is to isolate all important mathematical data from the pictorial descriptions of these problems. In the end, your diagram should include any given angles and dimensions, all forces including weights whose magnitudes and directions are specified or implied. Any unknown angles and forces should be labeled with directions of forces indicated by arrowheads. If you're unsure of the direction in which a force acts, assume one. Let's look at example 3.1. 3 packages, A, B, and C, are stacked at rest in a static position on a table, as shown in figure 3.2. If the package weights are 15 pounds for A, 40 pounds for B, and 65 pounds for C, respectively, what contact force do you think exists between packages A and B? Between packages B and C? Between package C and the table? Draw a free body diagram of each package and show algebraically what the actual value is for each contact force. We begin by separating A from B, B from C, and C from the table, as indicated in Figure 3.3. Because each pair of surfaces represents a point of physical contact, Newton's third law tells us that these surfaces exert equal but opposite forces on each other. Therefore, we draw the force pairs FAB, FBC, and F-table as shown. How do we know in which direction to draw these forces? On more complicated free body diagrams, we often simply guess at the correct directions for each force. However, here our own experience should tell us that the weight of each package pushes downward on the package or the table below, whereas the lower packages and the table itself must push upward to support the cumulative weights above. Our forces, then, are drawn downward on the top of surfaces B, C, and the table, and upward on the bottom surfaces of A, B, and C. The weights of A, B, and C, assumed to act downward at each package's geometric center, are also drawn on the appropriate package. In its free body diagram, then, each package is now disconnected from any other object. It is free in space, an isolated or free body, but the effect of every adjacent object is retained in the form of a contact force. For the packages to physically remain in equilibrium at rest, the vertical forces that act on A, B, and C must balance. In other words, on each package, the sum of the forces up must equal the sum of the forces down. By inspection of the free body diagram for A, the force AB equals the weight of package AB above. The force exerted on FBC that's coming from both packages A and B will be equal to the weight of the package B plus the force AB, which will be 55 pounds. The forces exerted on the table will be equal to the summation of weight of the boxes on the table, which is 120 pounds. In the next example, the 12.5 kilonewtons block is supported by cables as shown in Figure 3.4a. Draw the free body diagrams for the block and for point B. First, consider the block as a free body. The force T of the cable acts upward along the cable away from the body, and the 12.5 kilonewtons weight of the body acts downward toward the center of the Earth. The two forces act along the same straight line. They form a collinear force system. Because the block is at rest, the forces are in equilibrium, and the resultant is equal to 0. Therefore, T minus W equals 0, or T equals W equals 12.5 kilonewtons. So, the tension in the cable will equal the same weight of the block. But remember, if we are drawing a free body diagram for the block, you only need to show the block first. Then you need to show the forces going in or outside the block. The second thing is, if you are drawing a free body diagram for point B, the vertical cable can be thought of as transmitting the weight of the block from the block to point B. A cable can support a tensile force. Therefore, in the free body of point B in Figure C, each cable is in tension and acts away from point B. In example 3.3, consider a 100-pound block that is supported by a cord and smooth plane, as shown in Figure 3.7a. Draw the free body diagram of the block. We isolate the block as the free body figure B. 3 forces are acting on it. The tensile force T on the cord acts along the cord and away from the body. The reactive force, Nr, of the plane on the block acts normal to the plane at the surface of contact and toward the body. The 100-pound weight of the body acts from the center of gravity, G, downward toward the center of the Earth. The lines of action of the 3 forces intersect at point G and thus represent a concurrent force system. In Figure C, we move force Nr along its line of action so that all the forces are directed away from point G. Free body diagrams can also be used to find the internal forces carried by an object. Consider the rigid weightless link AB in equilibrium. An imaginary cut through the link at any cross-section along its length causes the internal forces exerted by each piece of the link on the other to appear as an equal but opposite pair, Fi. For equilibrium of both pieces, these forces must be in the directions shown, and Fi must equal F. AB carries constant load F everywhere along its length and is in compression at all points. Flexible members, such as cables, ropes, cords, and other strings, can support forces that tend to stretch the member, creating a condition known as tension. Cutting the member at any point reveals the constant internal tensile forces Fi. The use of free body diagrams can help us analyze the forces at any point in a system. Weight W is suspended by a cable supported on a frictionless pulley. Knowing that internal forces in the cable are constant, T, the member can be cut at points such as A, B, and C to begin construction of multiple free body diagrams to aid in our analysis.